Okay, time to start. Good evening, everybody. So it's my honor and privilege to welcome everybody to this wonderful event. So our annual Dame Kathleen Oleron Shaw lecture. So before, I particularly want to greet the members of Dame Kathleen family present here. Thank you for coming. So, but before I say anything, anything else, I need to make some safety announcements. So, concerning fire safety, if you hear the alarm sounding, please follow the voice instruction, because this is two-stage alarm. So you need to look for instruction. When asked, if asked, to evacuate the building, do not ask the attendees. We ask the attendees to vacate by the nearest exit and make their way to the marquee area in front of Williamson building, which is the building next to this one, for safety and not obstruct Oxford Road. And your nearest fire exit is the stairs next to the entrance, so this side or that side. Now, in the case of first aid, if any instance that first aid assistance is required, please follow the instructions on the first aid triage on the corridor outside the room. So there's some poster there. Okay, so hopefully we will not need any of these. One other announcement on different notes, so there will be wine reception, refreshments and drinks following the lecture. So everybody is welcome. Now, well, I would like to say that we gathered here for this exciting lecture that we do every year, named after Dame Kathleen Oleron Shaw. So let me say a few words about Dame Kathleen. So Dame Kathleen Oleron Shaw, born Kathleen Mary Timpson, was born in Withington in Manchester in 1912. She went to Somerville College in Oxford at the age of 19 to study mathematics. And she completed her doctorate in Oxford in 1945 on critical lattices. And she wrote 5 original research papers, which for her meant that she didn't have to write a separate thesis. So she earned her PhD without this separate thesis. She married Dr. Robert Oleron Shaw in 1939, and after World War II, so the family stayed in Manchester, and Dame Kathleen worked as a part-time lecturer in the mathematics department of this university when it was this department of Oxford Road. Dame Kathleen also became heavily involved in politics, particularly relative education. She served as a conservative councillor for Ashholme for 26 years, and she was Lord Mayor of Manchester in 1975 to 1976. She was made a freeman of the city of Manchester and was an advisor to education, on education to Margaret Thatcher's government in the 1980s. Well, she was probably best known in mathematics for her work in magic squares, but also has a great reputation as astronomer, and the observatory at Lancaster bears her name. She was passionately committed to encouraging interest in mathematics amongst young people. Well, she had been deaf since the age of 8, and she can be an inspiring model because of that. It is interesting to know that at her Oxford interview, she was lip reading, and so she hidden her illness. And before she was not admitted to Cambridge, she was interviewed at Cambridge, but they had an impression that deaf people cannot progress sufficiently, and so she was not admitted there. And Dame Kathleen held honorary degrees from both Victoria University of Manchester, which was, well, predecessor of this university, and also UMIST, another predecessor of this university. And she was a long-standing friend and supporter of mathematics in Manchester. And there's a lot of activity actually in Manchester mathematics related to her name. Apart from this, not only this lecture, but this lecture in particular. And so this lecture is a prestigious annual lecture, which was, I think, it started when Dame Kathleen was still alive in 2007. And it's aimed to appeal to anybody with interest in mathematics. So this is just a skeleton that one can say about Dame Kathleen, and I particularly encourage the students to read more about her, read her biography, and you can learn quite a lot from that. Okay, and now let me ask our head of department, Professor Andrew Hazel, to introduce the speaker.
Thank you and welcome. It's a delight to see so many people here. This is the first in-person Kathleen Orenshaw lecture we've had for 3 years, I think. Well, 4 maybe. The last one was in 2019. So I'm Andrew Hazel, I'm the head of Department of Mathematics, and it gives me great pleasure to welcome Professor Kevin Buzzard from Imperial. Kevin showed very early promise as a mathematician, getting a perfect score in the International Mathematics Olympiad, so a gold prize in 1987, I believe. He followed that by a BA and then a PhD in number theory from the University of Cambridge, and then was appointed to a lectureship at Imperial in 1998, then promoted to professor in 2004. He's won a number of prizes, a Whitehead Prize in 2002 from the LMS, a Senior Barrett Prize in 2008, and he's an invited speaker at the International Congress of Mathematicians in 2002. And recently, he's been working on this question, you may have seen some of it in the news as well, about will computers replace mathematicians? How can computers help with formal mathematical proof verification? And he's even been involved in a project with undergraduates to get them to use computers to check their work. So it's a real pleasure to have Kevin with us tonight, and I look forward to his lecture on will computers replace mathematicians?
Thank you for coming. I can look down here. Oh, great. So I'm giving a lecture, apparently, and it's about the different ways that mathematical researchers use computers. So there's some traditional ways. You can kind of see clues on the left there. There's traditional ways, and then there's some new ways. That's where we're going. Mathematicians, they do use computers. They've been using computers ever since computers existed, but actually they use them in more than one way. They use them in different ways. So what are the various ways that mathematicians use computers? One way, sort of common throughout applied mathematics and engineering and lots of other places, is to model reality. To model some kind of physical system. Another way is to do long and boring computations that humans don't really want to do by hand. And then so those two are old ways. And then here's one of the new ways. They've been using neural networks to give them ideas. So that's a novelty. And also recently they've been using interactive theorem provers, whatever they are, to digitize their knowledge. So I'm going to go through these 4. That's the talk, really. Those sort of a brief summary of what's been happening in these areas, and furthermore, sort of ends with just some speculation about how people are trying to put these things together and make even cleverer computers. So that's where we're going. So let's get started with modeling reality, which I'm not going to say much about because it's sort of a very traditional and well understood application of computers. So computers have been modeling reality since computers existed. One of the earliest computers was the EDSAC-2. This was a computer that the University of Cambridge bought in the late 1950s. And person in Cambridge buys computer would not be a headline nowadays, but breaking news, New Scientist 1957. Person in Cambridge buys computer. This is regarded as newsworthy. So the EDSAC-2, it didn't quite work when they got it. They called it the EDSAC 1.5, but after a while, it became the EDSAC-2. And what was it being used for? So important questions that somehow couldn't be answered without computers. So for example, sort of current models of plate tectonic theory were somehow came out of this early calculations done in the EDSAC-2 in the early 1960s in Cambridge. So this thing was huge. It was the size of it wasn't as big as this room, but it's bigger than most of the rooms where you live. And it had like 6,000 valves. So it had like a kilobyte of memory. It was sort of farcically, incredibly slow. And but yet it was good at doing repetitive. It was good at doing exactly the kind of thing that humans didn't want to do, which was boring, repetitive calculations, given a lot of data. And of course, so that was just the beginning. So, these very early computers were modeling aspects of reality, and nowadays you get bespoke computers that were built specifically to do things like predict the weather, because the weather is extremely hard to predict. This sort of this chaos theory, which was also discovered by because of computer simulations. This idea of very, very small perturbations of the input, like a butterfly flapping its wings, can cause very, very large deviations in the output. This is the joys of chaos theory, which makes it extremely difficult to predict the weather. So people build bespoke, extremely, most powerful, kind of up there with the most powerful computers in the world, just to model the weather. But as I say, this is a traditional usage of computers, so I'll say no more about it. But I do want to say more about doing boring computations, because this is somehow ideal. So how long have we been using computers to do boring computations for? So option 1 is decades, but the more unlikely option 2 is centuries, which sort of seems ridiculous, because obviously centuries ago computers didn't exist. And yet, if you dig out, here's a quote from John Napier, the guy that made the first log tables. When he'd finished doing them, he knew exactly what needed to be done to make better log tables. And so he suggested that the learned, who perchance may have plenty of pupils and computers, would be able to construct better tables of logarithms. And he then went on to explain what needed doing and how to do it. So John Napier seemed to think that people in the 1600s had computers, but what they actually had was that they were humans at that stage, right? They were just people that were doing calculations because they needed to be done, because industry and engineering were demanding computations, and so somebody had to do them, and we didn't have computers. So we did have computers, we had humans that could do them, so they called them computers, people that could compute. And in fact, throughout the history of human computing, most computers were women, because women were cheaper than men. You could pay them less, and they weren't obviously any worse. So why not use women? So there's a fabulous, I won't talk about it here, but there's a fabulous Wikipedia page on the Harvard computers, which were a group of women from the 1890s who were working in the astronomy lab at Harvard University, sort of interpreting the data that they were getting in, trying to work out what stars were doing and how the skies worked. And these people would be hired, as I say, a band of women. These women were hired to do grunt work. But what actually happened, of course, was they then started sort of collaborating with the scientists who were doing the science, and ended up doing things like getting PhDs in astronomy and writing joint publications and things like this. So this was some incredibly weird way in to astronomy. If you were when this was realized that this was what was going on, some women offered to start working for free at this place because they realized it was a way into research. So there you go. Computers used to be women, but then then they were replaced by machines. So here are some men, 2 men who worked out all the prime numbers less than 408,000. And prime numbers were sort of mysterious things, so they wrote a book. Prime factors, they factorized it, so every number less than 408,000, they broke it down into prime factors. And so now I know that some of you are desperate to go away and read this book, so spoiler alert, I'm going to show you a page from the book. I'm going to show you a page, this is the middle. And this is supposed to be numbers, but obviously the vast majority, looks like somebody who's gone mad, really. But it took me a while to work out what was going on. And this is indeed a list of lots and lots of factorizations of numbers. So let me just tell you briefly what's going on here. So we're starting. Firstly, they didn't do any number which was a multiple of 2, 3, or 5. If 2, 3, or 5 went into your number, you were expected to spot that yourself and divide it out and look for the new number in the table. So they only covered numbers that weren't multiples of 2, 3, or 5. So we're starting at 204,000. So the first one is 204,001. And it says sort of tau Gothic MU. And what's actually going on there is that 204,001 is a product of 3 primes. It's 7 times 151 times 193. And every time you get a new prime, it gets a letter, you see. And these are small primes, so they had nice simple letters. And then the next number, because 204,002 is a multiple of 2, 204,003 is a multiple of 3. The next one that isn't a multiple of 2, 3, or 5 is 204,007. And there they write the number, 007. That means that 204,007 is prime, and it's prime, so they give it a new letter. Even though actually they've just gone halfway beyond. That didn't need a letter, because twice it will not be in the book, because the book starts at anyway. I only just spotted that. They've given it a letter anyway. If I'd started a third of them, anyway. And then you see this one here, 204,011, that'll be that one there. There's no 011 mentioned because it's not prime. And those are the codes of its prime factors. So it goes on like that. So at the end of the day, what you have, well, amongst other things, you have a list of all the prime numbers less than 408,000, and so you can count them. So here's a question: how fast do the prime numbers grow? Right? How many prime numbers are there, less than 1,000? How many prime numbers are there less than 10,000? How many prime numbers are there less than 408,000? Nowadays, you could just write a computer program to tell you the answer instantly. But these were hard questions when the only computers were humans. So approximately how many prime numbers are there less than n? Well, suddenly we've got all the answers for n, all the numbers up to 408,000. And Legendre looked at them and decided that it looks like it's n over log n. That's what it looks like from the tables. And that became the prime number conjecture. And it took 100 years to prove. And it turned out to be true. And that's now called the prime number theorem. But the discovery of the statement was because of computers, human computers. So I mentioned the EDSAC-2, and there were all these people doing plate tectonics 9 to 5. But when those people left, Birch and Swindlers and Dyer used to sneak in the evenings. I've heard this story firsthand. Swindlers and Dyer used to show up at 5 p.m. when the plate tectonics guys were going, and hand a bunch of punch cards to the operator of the EDSAC-2, who would then run his programs overnight, and he would show up at 9 a.m. the next morning to get the printout. And sometimes the printout would just say error on punch card 37, and they'd have to then go back and get these crazy bits of paper that they had in those days and try and work out which hole he'd put in the wrong place and put it in the right place. So Birch and Swindlers and Dyer, they weren't doing anything as serious as plate tectonics. They were just counting the number of solutions to cubic equations in 2 variables, modulo prime numbers. So they were just working out, they were counting how many solutions there were to this equation, modulo 2, modulo 3, modulo 5, and getting nice big tables that this computer was generating once the punch cards were right. And once they got the tables, they drew some graphs. And then they looked at the graphs, and then they had a eureka moment, and then they made a conjecture. And the conjecture is now called the Birch and Swindlers and Dyer conjecture. And in some sense, it changed the way people looked at some aspect of mathematics. It showed some profound link between algebra and analysis that people hadn't really spotted before. And the conjecture is still open. It was made in the 60s, a couple of years after these computations were done. And it's still open. But the prime number theorem took 100 years to prove. So maybe this will take 100 years to prove as well. So this is a profound conjecture, which is one of the most important conjectures in mathematics. It's one of the Clay millennium problems. You get $1 million if you prove this conjecture. But computers were an integral part of the discovery. So there we go. So at the very beginning, they were counting solutions to cubic equations, but nowadays mathematicians just use them to make tables of anything they can think of. So elliptic curves, knots, graphs, finite groups, number fields, certain low-dimensional algebra. Those were all the things I could think of when I thought about this question for about 30 seconds, like the tables I've seen. There's plenty more tables out there that I don't even know exist, which mathematicians have made. And what do these databases look like? Typically, you get the thing that they're classifying, so a knot. Maybe we'll look at a database of knots. That's just like a piece of string in some tangle with the ends joined together. And then for this knot, mathematicians will have been able to work out some invariants, like some real numbers or some integers associated to these, to every knot. And so they'll list the invariants. So let me see. I don't know. I daren't use the internet. Let me just, there we go. Look, so there's a table I previously went to on the internet when I definitely had internet. So what is this? There's just a bunch of numbers. It looks very boring. But actually, if I click on one of these things here, let's see if we can get the internet to work. There we go. So that line of the table I just clicked on, it was about that knot there. And there's some drawings of the knot. And there we go, there's a little 3D thing. You can play with the knot. And if we go back here, that was knot 7.2. So there you go, knot 7.2. Apparently it's got signature -2 and volume 3.33. You see, so people are computing invariants of these knots, and then they're tabulating them, and then other people can use them. So that's a great use of computers, really. Oh, there we go. That was in case the internet didn't work at all. So far, what have we learned? Computers can model reality, and they can also be used to make large databases. And sometimes those databases can inspire humans to do brilliant things, like come up with the prime number theorem or the Birch-Swinnerton entire conjecture. So that's where we are so far. But actually, there's another reason that we might want to do long and boring computations. Like some people would say, well, who cares about tables? We want to prove, we're mathematicians, we want to prove theorems. You know, Pythagoras is famous for his theorem. We want theorems, and tables aren't going to prove. Tables might disprove a theorem. You find something that contradicts something that people believe. You might have disproved a theorem, but you're probably not going to prove a theorem if you have to check infinitely many cases. But it turns out that actually you can use computers to do that as well. So this is now called a computer-assisted proof, and there used to be a very small number, but now the number of computer-assisted proofs is growing. So what is a computer-assisted proof? The idea is, at some point in this proof, it's a rigorous mathematical proof, but at some point you reduce the question to a very long and tedious, boring calculation that you don't want to do by hand, but you can get a computer to do instead. So the first computer-assisted proof is a very famous proof, the proof of the four-color conjecture. So what does the four-color conjecture say? This says that if you draw a map on the plane or on a sphere, then the theorem is that you can colour in all the countries with only 4 colours, and if 2 countries are next to each other, they'll have a different colour. So if 2 countries touch just at a point, like you could imagine a pizza. If 2 countries that touched at a point had to have a different colour, then the 4-colour theorem wouldn't be true, because you get a pizza and you chop it into 8 slices, and all those 8 slices touch at the centre, so they'd all have to be different colours. But you're allowed to touch at a point and be the same colour, but you can't touch along an edge, like a line. So that's the theorem. This was a very old conjecture about maps, basically. It was somehow known to cartographers for centuries, but mathematicians couldn't prove it. And in 1976, Apple and Harkin, they came up with a technique which reduced the 4-color conjecture, which is a conjecture about infinitely many graphs, right? It's not a problem you can solve with a computer. But they did some maths and managed to reduce the question to a finite problem. And then the finite problem you can kind of do by a brute force computer check. But the finite problem was kind of annoying. The finite problem involved taking a list of 2,000 maps, or graphs as I've called them here, 2,000 graphs, and then they had to check that this list of 2,000 graphs had certain properties. And it was too tedious to do this by hand, and so they used a computer. So there you go. So this was the first time that a computer was used not just to make a database, but to prove a theorem. So this was a new kind of proof in 1976, and of course it made people, questions were raised, right? Because for the first time we have a proof of a mathematical theorem, but the proof is in some sense not, part of the proof is not human readable. Part of the proof says, now you have to do a gigantic calculation, and the computer did it and said the answer was yes. This made people think, what is a mathematical proof? Is a proof supposed to just say, yes, this follows from the axioms, or is it supposed to give you some kind of idea as to why the theorem's true? So different people might have different opinions about this. And another consequence, of course, is that this new kind of proof, there's an element of risk involved, right? You write down a proof, a normal human-generated proof, and then you might think it's right, and then you show it your friend, and your friend says, actually, how'd you get from there to there? And they find a mistake in your proof. But with this thing here, you've got this computer program, and mathematicians might not be able to understand the computer program, because it's 1976, and computers aren't on the syllabus yet. And the computer says that this is the right answer, but in 1976, you're still aware that these things might have bugs, right? If the program has bugs, then the program's done the wrong calculation, and your theorem isn't actually proved yet. So this raises two questions about what a proof really is, and I'll come back to those questions. I'll come back to those questions later. But that was sort of when it started. That was when the genie was out the bottle in 1976. And now I'm just going to tell you about several more examples of things kind of, in some sense, getting worse and worse. So the Kepler conjecture, this was raised. The issue is how to best carry cannonballs on a ship, or how the best way to put spheres in a box. This is the idea. And if I give you a bunch of snooker balls or something, and then asked you to pack them into a box, you would figure out pretty quickly, you make a little triangular grid on the bottom, and then for the next row, you make another triangular grid, and you put the spheres in the holes in the first one. It's somehow not that difficult to guess what the best way is to put spheres in a box. But for centuries, mathematicians were unable to prove this thing that seemed, greengrocers had known forever. But mathematicians couldn't prove it. So it was one of these frustrating things where it kind of felt obvious but hadn't been proved. But one of the things that mathematicians do when they can't prove something is they decide to generalize it. And so of course, you can start, instead of, why stick to 3 dimensions, right? Why not try 24 dimensions instead? So indeed, for every n, there's a question, what's the best way of packing n-dimensional spheres into an n-dimensional box? And for almost all of those questions, the answer is still completely unknown. And Kepler's original conjecture was about n equals 3. So here's Marina Wiesowska. And earlier this year, she got a Fields Medal, which is the highest award you can get in mathematics, basically. And the reason she got a Fields Medal was because she managed to work out what was going in dimension 8. Why 8? I mean, why not 4, 5, 6, or 7, all of which are still unknown? She had a brilliant idea, which managed to solve the conjecture in dimension 8. So now we know how to put 8-dimensional spheres into an 8-dimensional box in the best way. And in fact, about a couple of weeks later, her and some others working with this brilliant new technique also managed to solve the problem in dimension 24. So if you know any 24-dimensional people, anyway, that's what mathematicians do. But the thing about her proof was conceptual, right? Her proof was human understandable. So it's a brilliant piece of work because you can read it, and at the end of it, you kind of know why it's true. So hers was not a computer-generated proof. However, this chap here, Thomas Hales, about 20 years earlier, he managed to solve the problem in dimension 3. And there you get, there's a picture of the best way to put tennis balls on a table. And what did Hales do? Hales solved the original conjecture, the 3-dimensional conjecture. He proved that the greengrocers were right all along, with the result that now we know the answer in dimensions 1, 2, 3, 8, and 24. There's our some state of human knowledge. The total human knowledge for how to put spheres in boxes. But 3 is known, and that's good news because we happen to live in 3 dimensions. But Hales's proof was a computer proof. He did some brilliant mathematics and reduced the problem to a finite check. But the finite check wasn't 2,000 things, it was 70,000 things this time. 70,000 non-linear inequalities, each in some small region of the closed unit ball in R3. And 70,000 non-linear inequalities is kind of too many to do by hand, and so of course he wrote a computer program to do it. And then he sent this to the best maths journal, the Annals of Mathematics. And the Annals of Mathematics sat on it for several years because they weren't quite sure what to do with it. And the referees weren't quite sure if they could, guarantee that these 70,000 calculations which had been done by computer, couldn't guarantee that they were correct. And in the end, they did publish the paper and remarked they were 99% certain that his proof was right. And I think that really annoyed Tom Hales. We'll get back to him later. But so there you go. And now here's an example from more recently. Harold Helfgott proved that every odd number, which is 7 or more, is the sum of 3 prime numbers. So it was known that there were only finitely many exceptions for a long time, since maybe even the 1930s. And it was known that there were sort of no exceptions above about 10 to the 60 by the 1950s. But 10 to the 60 is too high to count up to. But Helfgott managed to tweak the bounds and pull the calculation down to 10 to the 30. So Helfgott's proof looks like this. If n is an odd number bigger than 10 to the 30, then general theory can do it. And if n is an odd number less than 10 to the 30, then we can just check it on a computer. And that's a vast amount of computations now, right? He didn't do 10 to the 30 computations. That would take too long. Actually, yeah, we're getting to the point in life, actually, where 10 to the 30 computations might be becoming reasonable or on the horizon. He actually did far fewer computations. He relied on previous work that had checked the usual Goldbach conjecture up to 10 to the 24. But what the point I'm trying to make with this slide is that 10 to the 30 is a massive number, like sort of a million or something. It's inconceivably, it's far too, humans are not going to check 10 to the 30 things, right? Even if, in theory, humans, if you put me on a desert island for 10 years, I could check the proof of the 4-color theorem, but I couldn't check this. So that's where computer-assisted proofs are now. They've sort of gone beyond, the realm of the human. So there's a summary of these two traditional methods. Computers have been used to calculate data, and sometimes the data inspires us. It inspires us to make conjectures, and sometimes the data can be used to complete a proof. But nowadays, there's computer-assisted proofs which are far too long to be human verified. Actually, Marijn Euler has some even more terrifying examples, kind of proofs that take terabytes to store. So now I'm going to move on to the 2 new methods. So we should be halfway through. Oh, that's good. We are. I'm slightly behind. Right, I'll speak more quickly. So now I'm going to talk about 2 new ways of using computers in mathematics. And the first one is this idea about using neural networks. So the prime number theorem, how did it work? Humans made the tables, and then humans spotted the pattern, right? And the Birch and Swindon and Dyer conjecture, how did that work? EDSAC2 made the tables, and humans spotted the pattern. And so if computers are going to take over, then clearly the next thing that should happen is that the machines make the tables, and then the machines spot the pattern. So we're not there yet, but what happened, what DeepMind managed to do last year was that somehow a machine-human collaboration spotted the pattern. So I'll tell you the story. So it was in Nature. It's lovely to see pure maths in Nature. It's quite difficult to sell pure mathematics often, but there we go. It was in, it's been a good couple of years because there was some work, there was some interactive theorem proving work that was in there, and now there's DeepMind stuff as well. So there we go. DeepMind's apparently AI is helping untangle the mathematics of knots. So what's going on here? So this is a paper. You can read the paper. It's on the archive. And so who are the authors? Juhas and Lackenby, they're mathematicians who work in the University of Oxford in knot theory. And Davies and Tomasev, they're computer scientists that work at DeepMind. So it's a truly interdisciplinary paper. And so here was the idea. We've got these big tables of knots and all their invariants. So the idea was maybe you could feed these tables to a neural network which can try and spot some patterns, right? And so we don't really just want it to spot some patterns, we want to spot some interesting patterns. And let me go back Let me go back to that table of knots. So here's a table of knots. And you can see some of these invariants are real numbers, right? This column here is just full of real numbers. Whereas this first column here, the signature, is clearly, that's full of whole numbers, right? So there's whole number invariants, which I'm going to call algebraic invariants. And then there's real number invariants, which I'm going to call geometric invariants. And typically they're computed in very different ways. Like the geometric invariants, you look at the hyperbolic three-manifold associated to the knot. I don't really want to go into details, but there's two kinds of invariants. And so what would be an interesting relation between these invariants, if we found some relation that related discrete invariants to continuous invariants, then or algebraic invariants to geometric invariants, then that would somehow be regarded as interesting by the humans. So DeepMind tried to predict some of the algebraic invariants just using only the geometric invariants. And the thing that they had success with was the signature, the thing that was in the table, the signature of a knot. So this is a whole number, and the question is, can you guess the signature of a knot just from all these real numbers that are attached to the knot by mathematicians? So the way a neural network works is that you take your table of 1 million knots and their invariants, and then you take like 90% of them, and that's your training data. And you tell the system, look, here's loads of examples, here's the invariants, here's the geometric invariants, and here's the signature, and that's how the pattern works. And the neural network looks at that and goes, okay, let me try and figure out what that function is. So it churns away for a bit, and then it says, okay, I've got it. And then you give it the 10% of the things on the list that you're holding back, and you say, okay, now here's a list of geometric invariants, why don't you guess the signatures? And it gives out a bunch of guesses. And typically the first time you do it, the guesses are sort of woefully inaccurate. And then you say, okay, so this was your score, this is how badly you did, so now maybe you want to rethink. So then the computer's like, if I tweak all these parameters, the neural network, you then tweak the parameters of the neural network to try and make your error go down, and then you start again. And you keep going like this, and eventually the network, either the network, it just remains hopeless, and it just guesses answers and it's no better than random, even after you've trained it, or it gets the hang of it. And for this particular occasion, for this particular problem, the network seemed to get the hang of it. So that was exciting. So it had signatures and geometric invariants, and it figured out how to guess the signatures. And then they had to try and figure out what it was doing. So then you have to ask the network, which geometric invariants are you actually most interested in? Which are the ones that your incredibly complicated, linear algebra thing is doing? But the DeepMind people managed to do this and work out which of the geometric invariants were most significant in their algorithm. And so then, once the humans knew this, they then started thinking about what the relationship was. So they know that there's these three real numbers and this one whole number, and there's supposed to be a formula. The computer claims that there's a formula. And they had to find, it didn't say what the formula was, but they could just see that it must have found some formula because it was getting good at predicting them. And so the humans took over, and they looked at the data, and then we got a conjecture, and then we got a theorem. The humans managed to prove it. So it's humans and computers working together. So there's the theorem. Twice the signature. They made a new geometric invariant called the slope, which was just the ratio of two old geometric invariants. And the slope was very close to twice the signature, and in fact the error that could be bounded by other geometric invariants. So there's a new theorem in knot theory from last year, and the proof was certainly all done by humans, but the statement was a human-computer collaboration. And as I say, one thing it's got going for it is you feel like it must be profound because it's relating algebraic invariants to geometric invariants. So there's that, and I thought I'd give you one more example. This is Wagner, a group theorist, a graph theorist, was looking for examples and counterexamples in graph theory, and he trained a neural network as well. So again, we've got huge databases of graphs. So here's a conjecture from 2010 that was true for all the graphs in the database. If you've got a connected graph with at least 3 vertices, and the largest the eigenvalues of the adjacency matrix are a thing, the largest eigenvalue is lambda 1 and the matching number is mu, then apparently lambda 1 plus mu is at least 1 plus the square root of n minus 1. So where did that conjecture come from? That conjecture was made by a computer because people have been trying to get computers to do that sort of thing. So this is pre the sort of the neural network revolution. But the idea is you're only using simple things like addition and subtraction and square roots. So you can guess lots and lots of simple formulas, and 99% of them are rubbish. But the ones that don't get immediately rejected, you end up with conjectures like this. So this conjecture, it was made by a computer, and the evidence for it is we've got a big table of graphs, and it's true for all the graphs in the table. So how are you going to prove or disprove this conjecture? So Wagner decided to try and disprove it. So the conjecture is that this number here is supposed to be at least this number here, so we can look at the difference. That number there, take away that number there, and that difference is supposed to be at least 0. And so what we're going to do is we're going to give our neural network a reward if it makes that number very small. So let's take the negative of that number, and that can be the reward. So the neural network tries a graph and tries another graph, and then it looks to see what its reward is. Then it tries to figure out how it can make its reward better, and it starts fiddling around. And of course, if you manage to get that number negative, less than 0, then it turns out that this number is not bigger than or equal to this number, and you found a counterexample. So here's some. So that's a random graph. There you go. It's 19 vertices, and you draw edges randomly, and that's where you start. And then you see if the conjecture is true for that graph, and it is. And then you try and work out which way to go to make the conjecture. I want to get a bigger reward. So after one iteration, the neural network is already suggesting a far sparser graph might be an idea. And it goes on like this. And now it's suggesting that actually maybe no loops is a good idea. There's one loop there, this triangle. But apparently graphs with not so many loops is a good idea. Graphs that have, there's a couple of vertices there that have got a lot of edges coming out of them. They look like they might be a good idea. And eventually now we've got two nodes with lots of edges coming out of them, and they're very sparsely connected. And in the next iteration, they're just connected by one thing, but they haven't quite got the same number. I think one's got 1, 2, 3, one's got 7 and one's got 9. And in the final iteration, they both had 8. And that was where the neural network stopped. And in fact, that turns out to be a counterexample to the conjecture. So the computer was just looking, but sort of it was looking in a very different way to the way that humans look. It was looking for patterns that were somehow not so obvious to the human. And it found a pattern, and there you go. There was another, in some sense, even more interesting example, where it didn't find a counterexample to a conjecture, but the end result of the iteration was a graph. It had one vertex with 2 very long strings of edges coming from it, and then many, just one edge to another vertex, and that was it. And the computer really liked graphs that looked like that, and then the humans just took that graph and just added 100 more edges to this, 100 more edges of length 1 to this central vertex, and proved that the resulting thing was a counterexample. So the computer didn't find the counterexample, but it somehow found the picture, and the human, you look at that picture there, you kind of say, yeah, I see what's going on now, right? The picture, the first picture doesn't make sense. That picture makes sense. So the computer is somehow making sense of what's going on, right? And then, but somehow it's not doing it by itself, right? The humans are asking the questions, and the humans are interpreting the output. So it's humans and computers working together. So I shouldn't do long quotes, but I really like this long quote by Geordie Williamson, because I think this work proves something. And I think what it proves is, Williams is a brilliant Australian mathematician who was also involved in some work with DeepMind that I haven't talked about. But he's pointing out, you send your kids to school and they do their maths GCSE and they get given a number or a grade, and you kind of get the impression that maths is being scored on some sort of linear scale. But intelligence, what you need to do, research level mathematics, it's not a number. It's not a single variable. It's a multi-dimensional thing, right? And we know that, right? Because I'm sufficiently intelligent, whatever that means, to be a professor at Imperial, but I'm very poor when it comes to things like emotional intelligence. And so you can sort of see already, you know that there's different kinds of intelligence. And Williamson's suggestion is that AI is just simply going to be a new dimension, a new kind of intelligence that we will, in the coming years, learn how to harness. So, final part of the talk then. Well, yeah, before we philosophize about the future, what if you've got no database at all? What if you work with objects that are uncomputable, or they're infinite dimensional? Or what if you work in an area where computations have been done, but you're not convinced that they're going to tell you anything important? So there are still plenty of people out there working in maths departments that don't use computers in their work, and maybe a reason for this is that they can't see how things are going to fit in. So for those people, there's, again, something new that's been happening in the last few years. There's the theory of interactive theorem provers. So last 10 minutes, I'll talk to you about interactive theorem provers, and what they do is they turn maths into a puzzle game, a computer puzzle game. A computer puzzle game that I am completely addicted to, really. And so let me just, I won't start, if you get me going on interactive theorem provers, I'll just sit playing interactive theorem provers in front of you for ages. So I'm not going to fire one up. But let me show you the difference between an interactive theorem prover and a computer algebra system. In a computer algebra system, you can say things like, let G be this group, or count the number of elements of order 37 in this group, like do a concrete calculation. But in an interactive theorem prover, you can say, let G be a group. Right? You can have a variable that represents an arbitrary group. So it's somehow one level of abstraction up. It's not working with concrete structures. It's working with abstract structures. And interactive theorem provers, they give you this new possibility that instead of just getting computers to compute and to calculate, maybe you can get them to reason, like to prove theorems by themselves. So, to give an example, if I asked you to get a computer to compute prime numbers, you could write some Python code that just starts printing out all the prime numbers. And if you left it on for a very long time, it would just print out more and more and more prime numbers and give evidence that there's infinitely many prime numbers. But it could never prove that there's infinitely many prime numbers, because that's, you can't prove that by computing them, right? But in an interactive theorem prover, that's exactly what you can do. You can prove that there's infinitely many prime numbers. So it's a way of turning theorems into something a computer can understand. So basically, an interactive theorem prover is a computer language which is somehow sufficiently rich that it can understand the mathematics that we teach at universities and that researchers do. And once you have one of these things up and running, then a mathematical theorem becomes a level of the game. And the way to solve the level is to first of all learn the language of the theorem prover, and then work out a proof, and then translate your proof into that language. So there's interactive theorem provers. And one of the things I discovered about interactive theorem provers, just by experimenting with them 5 years ago, is that you can teach them to undergraduates. And the undergraduates can then use them. In fact, some of them very quickly learned how to, I was in 2017 when I entered this area, I didn't really know what I was doing, but I practiced over the summer, and then I started with the undergraduates, and within a few weeks it was clear that at least one of them, and possibly two of them, were better than me, which was nice, because having spent 20 years as a professional number theorist teaching them number theory and just being much, 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 much better than them, suddenly the playing field was sort of leveled, and these people were learning this stuff faster than I was, which I thought was very exciting. But not at all surprised. I did end up publishing a paper with 4 undergraduates, which I thought was quite fun. But in some sense, it's not surprising, right, that interactive, something that knows the axioms of maths can do undergraduate level mathematics. But one thing that we've proved more recently is that nowadays we can actually get these things to the boundary of modern research. So I'll say something about that later. But that's somehow the new thing about interactive theorem provers, is that I feel now that they're sort of good enough to go anywhere. So you can interpret all of the theorems and conjectures of mathematics as being like some kind of open world computer game. And you can imagine the paper proofs, the proofs that we see in the books, kind of like they're sketches of what's really going on. But they leave out details. So you can, if you like, you can think of them as concept art. Yeah, they're pictures of what this world should look like. What is this world, this universe that we're playing this game in? People would call it the Platonic universe. That would be one way of thinking about it. A place where 8-dimensional spheres actually exist is not the same as the physical universe. So it's quite a crazy place. But at the end of the day, how is this thing powered? It's powered by the axioms of mathematics and the rules of logic. And so the game is, if you've only got the axioms of mathematics and the rules of logic, then you have to make a city, right? The city consisting of all the theorems that we know. So we've got this power source, and so the early interactive theorem provers, the only thing you could do was just carefully prove everything by applying axiom after axiom and rule of logic after rule of logic. But they've got really good now, and you can write things the way they're written in the textbooks, and the computers can start filling in the details, and you write one line of code, and it becomes kind of 100 lines of applying axioms that you don't ever see, because that's what they've got good at recently. The power source, that's where the logicians go. I tend not to look in there, because most mathematicians don't actually know what the rules of mathematics are. They just sort of have an instinctive feeling as to how they work. So as I say, we've got all this paper literature, all these people that have claimed to have written down proofs of things. And of course, in most cases, they're exactly right. But you can just think of them as sketches, because just brandishing a piece of paper at your interactive theorem prover doesn't turn it into, you have to do some work, right? So you see, this is the problem, is that if you've got some glorious theorem or definition in your world, it's just sitting there with no power, not lit up at all, and you have to power it up by making that connection. Sorry, making that connection from the axioms to this mathematical object that you're trying to get working. So that's the game, really. And as I say, it can get quite addictive. Maybe I'm going to have a drink. Oh no! Look, whose water is this? Did somebody leave this lying around? Oh. I'm kind of desperate. Oh, there we go. That's much better. So there we go. We've got to prove a theorem. We've got to prove it from the axioms of mathematics, and we've got to prove it in this virtual world. That's the game. And so, in other words, we've got to construct a rigorous argument that proves that theorem from the axioms of mathematics. So that's what I've rigged it basically so I get to play computer games at work. Is what the moral of this story is. But it's a collaborative game. It's really good. There's lots and lots of other people that I hang out with on the internet who play this game as well. And of course, the moment somebody makes a new theorem, then everybody can use it, right? So it's a nice collaborative game. And as I say, mathematicians used to play this game on paper, but if you've played Sudoku in the newspaper, and you've made a mistake, and then you've crossed things out, and you've made a real mess, and then you download a Sudoku app on your phone, and you play it on your phone, it's kind of a much smoother experience. So this is the experience I'm having right now. Instead of doing mathematics on paper, I'm doing it in an interactive theorem prover. And it's just somehow, it's a new way of doing mathematics. So there's many of these games around. The version that I use is Lean, the Lean theorem prover, which is developed by Microsoft Research. And there's many other theorem provers out there, so you could try any of them and go and see what the worlds are. And of course, all the worlds are in very different states, right? There's some theorems that are proved in Lean but not proved in MetaMath, and then there's some theorems that are proved in MetaMath but not proved in Lean, and whatever. So all the landscapes are kind of different depending on what people have got round to lighting up. So each one of these interactive theorem provers has got a library, and Lean's library is called it's MathLib, which stands for Maths Library. It was named by computer scientists. So we're stuck with this zany name of MathLib, but as I say, it's my favourite computer game, and when we switched it on in 2017, there was nothing. There was some very, very basic results about finite sets, and that was about it. And one of the reasons that it kind of got good was that I encouraged lots and lots of people got involved, wandering around this game, proving theorems and lighting up bits of this world. but some of them were undergraduates at my university who I would just encourage to do it because I thought it was an interesting project. So what do these things do? What's the point of them? Well, in 2005, Georges Gontier, he formally verified the four-colour theorem in Cox. So the four-colour theorem was the first computer-assisted proof, and humans were sort of saying, well, what if there's a bug in the code, right? Then the proof isn't correct. So what Gontier did was he rewrote the proof in an interactive theorem prover. So in particular, he rewrote the code that does this calculation with these thousands of graphs. And then he proved that the code has got no bugs, because that's the kind of thing you can do with an interactive theorem prover. You can prove theorems. So you can prove that the code has got no bugs. So he gave a formally verified proof of the four-colour theorem right down to the axioms of mathematics. And as I say, some people regard this proof as ugly because it's not human comprehensible, but at least now we know it's bug-free. At least now we know it is a proof in the sense of being formally deducible from the axioms. And Tom Hales, who's still, who was annoyed, presumably, by this 99% certain comment, went off and spent 14 years of his life formally verifying the Kepler conjecture, the thing he proved about three spheres. Using a combination of two interactive theorem provers. But this was a sort of monumental project, a team of 20 people. So again, this is sort of another example of a computer-assisted proof where, to counteract the criticism that maybe the code has bugs, the idea is you can write it in an interactive theorem prover. And that was one of the main uses of interactive theorem provers, sort of pre the last few years. So as I say, these proofs might be unsatisfying, but at least we know that they are mathematical proofs in the sense that they follow from the axioms. So more recently, mathematicians are using them to prove theorems that don't rely on big computer calculations. So we're moving away from computer-assisted proofs and just proving theorems for fun. And I would say that nowadays, all of mathematics is in theory accessible to these things. And that somehow wasn't clear a few years ago, but I think nowadays we do know that. But if you take some, what's your favourite theorem? Like Fermat's last theorem is maybe my favourite theorem because my advisor proved it, and his advisor and ran off to Princeton and left me in the lurch as a PhD student with no advisor at all. But still, I forgave them because they proved Fermat's last theorem. And I would say that actually, sort of, if the community stays at the current size, and we just keep going making more mathematics, then it's going to take quite a long time. So as I say, I entered this virtual world in 2018 with two friends of mine, two people I've met on the internet, both also mathematicians. And we found that actually we were very much in the minority. It was mostly computer scientists playing this game. And that means that the kind of mathematics that's being done is somehow of a very different nature to the kind of mathematics that we're doing research in. So we decided to go on a campaign, and the campaign was to get to the definition of a perfectoid space, because perfectoid space has just been invented a few years beforehand by Peter Schultz. I mean, they've got a really cool name. That was one of the reasons we wanted to go make perfectoid spaces. And also, they're just one Schultz-Fields medal. So we decided we would make perfectoid spaces in Lean, and once we actually got going, we just went off on an adventure, basically, in this open world adventure game. Went down a route that no one had ever gone down before. And so about 8 months after we'd really started working on it seriously, we made it. And we lit it up, and it worked. And we kind of thought, that's a weird thing that no one's ever done before. But somehow, Schultz, who invented perfectoid spaces, wasn't fooled by this in some sense, because all we'd done was make one of his definitions. So he challenged the community to prove one of his theorems, something he'd proved in 2019 with Dustin Clausen. But fortunately now, there was only a few mathematicians in 2018 in the area, but by 2020 it was sort of catching on. So we put together a group of 10 of us, and off we went, trying to prove this theorem of Schultz and Clausen. So my collaborators, Komalan and Topaz, were the leaders of this journey, and did the vast majority of the work. I did some, but they certainly did more. And we started last year, and we got there over the summer. And it was absolutely brilliant. So that was what we did. We formally verified a vanishing theorem for higher X groups in the category of condensed abelian groups. So I'm not going to go through what all that means, but that's a thing, and not only is it a physical thing that you can see on paper, it's also a digital thing that exists in an interactive theorem prover. And it was brilliant. We just went to places that no one had ever been before, and I found it completely fascinating. And this is what Schultz had thought of it. He said, I found it insane that interactive proof assistants are now at the level that within a very reasonable time span they can formally verify difficult original research. So that's the last message I have. That's what interactive theorem provers can do now. In theory, they can understand all modern mathematics, but in practice we've still got a lot of work to do to build the world. So I need to stop. So I've got 5 more slides that I'll whiz through about how we can put these things together, right? Because that's how progress works. You understand what's happening now, and then you work out how to go further. So the idea is that instead of humans wandering around this virtual world, they want to make bots that wander around the virtual world for you, just making stuff for you. So how are these bots going to work? There's 2 components. There's automatic theorem provers. Those are just going to do easy stuff. Those are going to find proofs of simple things and not bother humans about them at all. So automatic theorem provers do the easy stuff, and then the neural networks are going to do the harder stuff. The proofs that are long, the idea is, let's use a neural network, let's train it on the internet. Let's get a language model, train it on the internet, and see if we can get it to write proofs. So it all sounds a bit ridiculous, really, and 2 years ago, I thought it was completely bonkers. But where is this research happening? Not in the universities. The research is happening in tech companies. OpenAI and Google and Facebook, they all have teams involved. We're trying to get computers to beat humans at mathematics. And the idea is you look at a language model. There are these language models that can just write news articles. Now you give it a subject and it just starts expounding upon it. So the idea of a language model is that the input is what we've just said, everything we've just said up till now, and then the output is what's the next word we should say to continue making sense. So that's the idea, and now you say, and now write some interactive theorem prover code, please, and you see what happens. So it sounds completely far-fetched, but actually, I was at a conference in Paris 2 weeks ago, and Facebook was showing off their latest version of this, and they've managed to solve a very small number of international mathematical Olympiad problems, and that's somehow, those are hard. Those are hard questions. So here's an example. So this is a very early IMO problem. Early IMO problems were easier than ones now. So this is from 1964. Prove that 7 doesn't divide any number of the form 2 to the n plus 1. And this proof obviously is sort of incomprehensible to you, but the point is, you can translate that into normal mathematics. And if I were to be given that and had to mark it, I would say, well, you've done this quite inefficiently. You've gone kind of a bit all the way around the houses. You could have shortened the argument here. But at the end of the day, this proof is correct. It's just a bit long-winded, so I will give you full marks. But that proof was generated by a language model, which I think is quite extraordinary. So it generates lots and lots of attempts, and most of them don't compile. But because this whole thing is running on a computer, you can say to the computer, is this a proof? And the computer can say, yeah, that one works. And you say, great, I've done it. And so now they're talking about getting robots to try and do the International Mathematical Olympiad. And so that would be an interesting development. So as I say, it was generated using AI and interactive theorem provers. But you have to be careful, because you follow some AI people on Twitter, and the next thing you know, you're going to be believing that they're just going to, computers are just going to destroy mathematicians. All mathematicians will be out of a job by the next decade. That's what some of the people say. But as I say, I'm a bit of a skeptic. I do think, like Williamson, I think that AI will give us a new dimension, but I don't think that they're going to, famous last words, right? I don't think they're going to steamroller over us. I don't think they're going to prove the Birchton-Swinnerton-Dyer conjecture, because actually, I don't think these things can even state the Birchton-Swinnerton-Dyer conjecture, because you have to analytically continue an L function. But at the end of the day, you can't stop progress, and what's happening here is that the digitization of mathematics has begun. And we don't really know where it's going. All we know is that we can now, in theory, digitize all mathematics. So digitization then. They digitized chess, and then we had a chess computer that could beat Kasparov. And they digitized books, and now we've got Kindles. They digitized audio, and now we've got podcasts. They digitized music. They digitized music, and then we got CDs. And CDs were just rubbish. That was like, what was the point of a CD? I'm looking at this in 1990 thinking, it's more expensive than a record. Yes, it's smaller. Like, some people say it doesn't sound as good. But, so why do I have to buy this CD? But the point was not the CD. The point was that it was digital. That was the thing. The reason Spotify exists is that if music's in digital form, you can just store loads and loads and loads of it on a machine and then send it to anyone in the world who wants it, as long as they've paid or are happy to listen to adverts. That's what makes the digitization of music such a revolutionary idea, right? You digitize something, suddenly it's more flexible. And in the lean community, we're digitizing mathematics. And we don't really know where it's going to go, but one of the things it will certainly enable us to do is to get neural networks involved even more strongly. But as I say, this new area is really still in its infancy. So what are we going to do? I can't see the future, right? How far can we go? I think the computers are going to help us more, but are they going to overtake us? As I say, I'm a skeptic, but at the end of the day, nobody knows. Thank you very much. Nope. Several people at the front here. There's people here, if you're interested.
So are these theorem provers able to do anything other than verify a proof? Are they able to generate unique proofs?
So the theorem provers by themselves, all they do is sitting there going, tell me the next thing and I'll check it's true from the axioms. So at the minute, mostly, certainly at my university, they're being used by humans who are literally translating known theorems already. But these companies are using AI to generate things. But at the end of the theorem provers just sit there going, tell me what to check next. Yeah, so it's the inputs which are changing.
Hi. So for one to start using these interactive theorem provers, one must also learn the language in which the proofs are written, right?
Yeah.
And so how big or small do you think a problem it is that that language is very different from the natural language of mathematics?
Well,
in respect of it, in respect of the interactive theorem provers being popular enough.
I mean, did you learn Python? Something like that? Lots of people have to learn Python. That's kind of different to human language, but it didn't stop you learning it. I don't know if these things are too different from... Did you play my game?
Yeah.
Oh, very good. I wrote a game called the Natural Number Game, which I wrote to get undergraduates interested in this stuff, and undergraduates do like it. But you only have to learn a small amount of you only have to learn a few basic tactics, and you can prove a lot of things about the natural numbers. I mean, I agree, not everyone is going to be interested, but I don't need everyone to be interested. I just need a small percentage of people to be interested. Because as long as the area keeps moving forward, things will continue to happen. So, you're right, it's hard, but I'm not too bothered.
Thanks. Hi, this is probably a continuation of the previous question. So when you talk about digitalizing mathematics, I'm interested to know, like, are you satisfied with the current form of how we are digitalizing mathematics in terms of how the current interactive theorem provers represent these theorems and their proofs? So I actually have experience using many of these theorem provers, and I'm curious to know, like, if, for example, in the future, instead of writing a whole paper, like I just published a PDF which consists of entirely of the code, which a computer will say it's a proof, then what form would you like? Do you think the current form suffices as a good mathematical publication, or what do you envision it to improve on?
Yeah, I think writing a paper that's just hundreds of lines of computer code would not go down very well. So yeah, what is a proof, right? Is a proof something that you're supposed to read and understand and learn from, or is a proof just something which is a formal derivation? You know, are you a formalist or not, right? And so different people will have different ideas. I think proofs are supposed to explain what's actually going on. So I think like that a great example of a proof that tells you absolutely nothing is that thing that I just had up here, right? Let's see if we can. This Facebook proof. There you go. Like I would regard that as problematic. But on the other hand, the code that I show my students doesn't look like that. The code that I show my students, for every line of computer gobbledygook, there's a line, at least one line, possibly sometimes more than one, of comments that just say, this is what's happening here. So I tend to, because I give courses in this stuff, right? So I state the theorem, and then I write a proof just in comments. Right? I write a proof in English, and then I say, and now our job is to translate this proof into the language of the prover, and then I sort of translate it line by line. And all I'm saying is that I'm just giving evidence to the idea that what these computers think of does correspond in some way to what we believe of as, what we think of as mathematics. I think that these things think about mathematics the same way as I do now. That's one of the reasons I fell in love with them, because I found a thing that thought about mathematics the same way as me and got fascinated by it.
There's a term that's being bandied around, which is the Minotaur model, where human with computer will always outperform a computer. I think that's in danger of being flipped.
Oh, you think? I think human plus computer is the best. They do this with chess, don't they? They've like human with computer is better than human and better than computer.
In many domains, it's said.
In many domains. Well, I think this deep minds. So there you go. There's computer by itself, giving a very inefficient solution to a not particularly difficult problem. But on the other hand, humans are just slow. So yeah, okay. So I think maybe, I don't know. I believe in Minotaurs. Then I think that, but I think at this point we're still trying to work out how to have a good relationship with computers. We don't quite understand what they can do, but yeah, maybe, I don't know. They're just adding another dimension. Go with the Williamson quote. We can think in one direction, they can think in another direction, and so now we can go in two dimensions.
Hi. Oh yeah. Are there any other sort of similar lean type projects like the liquid vector spaces stuff? Like, is anyone doing the Mochizuki ABC thing, or? No
one's doing Mochizuki because a large part of the mathematical community don't think the theorem is correct. So when Scholter said, prove one of my theorems, everyone's like, well, okay, he's got a Fields medal, so his theorem's probably correct. Yeah, this is difficult. There's this new work by Zhang on Siegel zeros as well, and people are like, yeah, why don't we just do that? And it's like, other people are like, yeah, what if it's not right? I mean, no one's got a clue whether it's right or not, right? It's 100 pages and it only appeared on the internet a couple of days ago. This would, yeah. These would be interesting projects, but the problem is, there's a practical problem, which is that this is young people with their careers on the line, right? So you're sitting next to Andreas, and I got him formalizing mathematics when he was an undergraduate, and he was one of the he was an early adopter. And I was very concerned at the time that these people, I was sort of leading them astray, and that they would be formalizing mathematics and not doing their homework properly and end up failing their degrees. And it was sort of, you know, I've just sort of led them to disaster like the Pied Piper somehow. But then people like Andreas managed to get PhD places, and you know, all that sort of crowd, you know, Kenny and Amelia and all these other people he knows all got PhD places. So to a certain extent, it works. You can get young people doing this stuff, and they end up sort of surviving in the system. But if you say to somebody, why don't we spend 5 years of your life typing in the proof of Mochizuki, and then they spend 4 years on it, and then they get stuck, then people are going to say, you know, do you actually, you know, where are your theorems? Where are your new theorems? We're all still judged by our theorems. So the question is how to manipulate the system so that people can take on large projects without sort of losing their jobs or failing to get jobs, because a lot of these people involved are postdocs. I'm the oldest person in this game by like a factor of 2. It's ridiculous. Everyone is a PhD student or a postdoc or a very young member of staff. And then there's me and just a couple of other people in our sort of 40s and 50s. So I think it involves an element of risk. And until we work that out, and that's a financial problem or a cultural problem, not a mathematical one. Like if somebody gave me money just to pay people to do this, and I could find people daft enough, I can, you know, but you know, if it was just a job and then at the end they left. But if people want a career in mathematics, this is a very risky way of going about it, and that's the main problem.
Perhaps I'll ask a question that will round it off a little bit. I've often had a theory that when you get these difficult questions, there isn't a solution.
Oh.
You stand and say, well, I'm a denier, or whatever it is you say, you're a skeptic.
Yeah.
In actual fact, what you are doing is a very important job, and you are redefining what a mathematician is and redefining what a computer is. And that tale ought to carry on, but it might look very different if you could be reborn in 100 years and look at what's happened.
Oh, yeah.
And I also think that one thing that we can learn from artificial intelligences of all kinds, it actually has a good chance of making us better humans. Because when we try and out with them, we'll finally work out what mathematics is, what intelligence is, what ethics is, what a curiosity machine is. All these things are big questions that we ought to move on to next.
Mm-hmm. I do wonder why these big companies get involved, and I think that they feel like they've solved board games. You know, there's an example of a problem that's been solved, because now computers are just better than humans at any board game. But they feel like they haven't solved mathematics yet, but it sort of feels like the next step. You know, they want to make computers that, you know, are intelligent, and they want to sort of try and understand what's actually going on. So in some sense, I think this stuff is a stepping stone, really. But if big business is interested, then, you know, there must be something to what you say. It must be important somehow. And perhaps my, you know, I'm focused on mathematics. Perhaps I'm being too limited, really. I don't know.
I'd like to ask, how prevalent do you think the self-learning of these computers are? Like, is it just for like spotting patterns, or is it more than that?
They can't even spot patterns. I mean, they can spot some patterns. I don't understand neural networks at all. They can, if you show them how to 100,000 sums of 2 10-digit numbers. So look, here's how addition works. Here's 10-digit number, add another 10-digit number, and there's the answer. You show it hundreds of thousands of those, and then you get it to learn, and then it learns addition. It can do addition. But then you do the same thing with multiplication, and you just can't get it at all. So it might be able to prove conjectures in graph theory or whatever, but learning how to multiply 2 10-digit numbers seems to be beyond it. So at the minute, we don't really understand what neural networks can and can't do, because some things they seem to be good at, and some things they seem to be sort of really much worse than you might expect a computer to be.
So it's relying on us to like teach it?
I don't know. It's relying on us to work out how to make better AIs. I mean, the word AIs exists for decades, right? But it didn't used to mean, now it sort of means neural networks. But before that, it just meant, you know, alpha beta pruning or something. It just meant, you know, getting a computer to do a bunch of grunt work. So the word AI will sort of continue to, evolve in its meaning, and that will be humans doing research, trying to work out new ways of solving problems. But yeah, it's really sort of in a weird state at the minute. In some sense, you can't really guess which problems they'll be good at, or at least I can't. So yeah, we need more research is needed.
Is the natural number game the best way for undergraduates to start working with this?
That's the way I try to get my students addicted to Lean. Yeah. So yeah, just search natural number game. Trust me. That's what you could read. I'm writing a book called Mathematics in Lean. You could read that. That would be something else. Or go to the Lean Prover community website and do the tutorials there. Those are all ways in. Maybe there you go. Do you want me to finish with an ad? Let's go here. Oh, I might not have internet. Let's try. Lean Prover. There it is. There's our website, the Lean Prover community. And there's there's how to install it and things to do. Anyone interested in interactive theorem provers? Go there. Is that the end?
We need to stop now.
Oh.
Thank you very much.
I'll be around for the next... Yeah. I'll be outside for the next 40 minutes.
Right. Let's thank the speaker again.